In the previous video, we started working on a problem of beam deflection. In particular, our case that we have this configuration right here. It's one sided engaged in the wall. Beam the other side, you have 2 kilonewton force, and the length of beam is 1 meter, and EI is equal to 1. And we work on this problem using the method of, they call it double integration. That means you simply use this equation. The second derivative of the deflection is equal to moment divided by EI, and double integrate this equation, apply boundary condition to find the solution. Here in this simple problem, the boundary condition was the deflection is 0 in the wall, and then also the slope theta is 0 at the bottom. We apply this boundary condition to find the deflection from x0 to 1. Now we want to solve a little bit more complicated problem. So let's consider the same beam, but we apply this force 2K, 2 kilonewton, exactly in the middle. So from here to here, let's say 1, 1, and this is 1. Now I want to find the equation of the deflected beam. That means when this loading applies, this beam is going to deflect like that, right? Then I want to see if this point is C, A, B, C. How much my neutral axis is going to go down at point C, or VC, the vertical deflection at point C. That's that's what I'm trying to solve for. So going back to the equations I had and I derived before, I simply write the second derivative of v with respect to x is equal to m over EI. And knowing that EI in this particular problem is 1, we simply get the second derivative of v with respect to x is equal to mx. Well, in general, if EI, this parameter right here, is not given to you, all you need to do is to go and look up the Young module of elasticity from the table for that particular material, and also you have to compute the moment of inertia. Well, we already talked about it in detail in vector statics, review material, so I'm not going to repeat myself, but in general, if you have a cross section like that, the first step you do, you find this centroid, which in this case is symmetric at the middle, and then you find moment of inertia Ixx, and this value is what you substitute here. Don't forget, it should be meter cube to the fourth power, right? If you have millimeter, you have to convert that. You usually end up with 10 to the negative 12. So right now my EI is 1, and this makes my job, the numerics, to be easier. So I have this equation that I have to integrate, but I note that here I wish I could disable this notifications from Gmail, but I don't think I can. Alright, so here what I need to do is to find moment versus x and substitute here, and then my problem is pretty much done, right? Double integrate, apply boundary condition, and I'm done. What are the boundary conditions? Boundary condition is the deflection at point A is equal to 0, or v at x0 is equal to 0, and also theta, the slope at A, is equal to 0. That means dv ex, x is equal to 0 is 0. These are two boundary conditions that I need to apply. In fact, look, if I take my x from A is my x, and I cut it anywhere here, I immediately realize that the deflection at x0 is equal to 0. The slope is 0. You see the slope right here? The slope is 0 because it's welded to the wall. If this point was pinned, you may have some slope like that. If there was a pin like here, like this, your beam would deflect like that. So you may have initial slope, theta, right? But in this case, you don't have, this is in fact your theta, which is the same thing right here, right? Let me draw this a little bit more clear here. So if you have a pin right here, and let's say you have a roller right here, your beam would deflect like that. So at this point, if I can choose another color, at that point you can have slope like that, and this is theta, theta, initial slope. But look, because it's welded to the wall at this point, you see that? You don't have a slope. So that's the reason I have this equation right here. Alright, so going back to the problem, so I have this equation, the second derivative v with respect to x is equal to m of x, and I have to double integrate. First I need to find my moment. How do I find my moment? Well, moment diagram. Okay, so how do I draw the moment diagram for that? Well, I know that I have two intervals, from x from 0 to 1, and then from 1 to 2, right? So if I consider my beam, before I section it, I need to take the entire thing as system, draw FVD. My FVD will look like AY MA, and then there is a 2K here, and this distance is 1, and that's it. The FVD for entire system. If I write moment equation about point A, summation of moment A0 equilibrium, I get MA positive, AY doesn't have a moment, and then negative 2K times 1 is equal to 0. That means MA is equal to 2 kilonewton positive. Right? So MA is 2, and by the same thing, if you write summation of forcing Y0, you get AY is equal to 2K. Right? So in fact, when I have this, then I can just say this is 2K, this is also 2K. Then I'll go ahead and do the sectioning. The first section is, this is your X, this is your X from any point between 0 and 1. Then my FVD will look like here. So I already have a 2K here, moment, 2K force up, from here to here is X that I cut, and this is the cut point. V at X, shear at X, M at X, and that's it. Don't forget, I don't include 2K because I'm just before that, okay? So if I write my moment equation, summation of moment equation about point X, and this is my point X right here, is equal to 0, I get mx positive plus 2k negative 2k times x is equal to 0. Mx positive plus 2k negative 2k times x is equal to 0. Solving for that, you get mx is equal to 2k times x minus 1. You just take it to the right side. 2k times x minus 1. That's your moment. So this is valid between 0 and 1. What about between 1 and 2? That means from here, when x, let's draw it here with green. We need probably another color, green, thicker. Okay, from here to here, x, between 1 and 2. What is the moment right there? Well, the answer is, again, you can take a system like that. If you want to use a brute force method, we have a 2k here, you have another 2k force up, and then you have a 2k right here, and at this point you have mx, vx. Yeah, you can go ahead and do that, but if you're smarter, you take the right side. Look at here. The right side, the system will look like this. So I'm going to have mx and a vx and nothing else. So what is the moment? Mx is equal to 0 for x between 1 and 2. So for x between 0 and 1, this is my relation. For x between 1 and 2, my moment is 0. So in fact, if I want to draw the moment diagram for that, let's use red. If I want to draw it right here, on top of that right here, okay? Between 0 and 1, I have this curve right here. So if I substitute number here at x0, I get negative 2k. There you go, negative 2k. This is my x, and this is my 0. And then at x equal to 1, which is right here, I have 0. Then after 1 also, I'm identical to 0 right here. So that's my moment diagram. Okay? So I know what to put right here when I integrate. Okay? But we know that here I have two completely separate intervals from 0 to 1, from 1 to 2. Okay? So when I integrate that, I have to do separately from 0 to 1 and separately from 1 to 2. And that actually causes two additional constants of integration, as you can see here. So let's write this problem. See if this is, I need this to tick. Yeah, this should be good. So I have two problems. D, get rid of this, d dx squared mx, which is equal to 2k times x minus 1 between x between 0 and 1, and the derivative, let's call this v1, because this v1 is going to show the deflection on our curve in the interval number 1. So this is interval number 1, this is interval number 2. So I have two different variables. So the second derivative of v2, which is showing my deflection in the interval number 2, which is between 1 and 2, dx squared is equal to mx between 1 and 2, which is equal to 0 there. X between 1 and 2. So this is a precise mathematical formulation. In fact, we are simply using the same formulation. Second derivative of deflection is equal to mx. But just because we have different moment relation, we have to consider this separately. And this is a trick to do this kind of problem. So what are the boundary conditions here? The boundary conditions are, look at where we have the connection to the wall. That happens right here. In fact, it's v1 that is equal to, at x is equal to 0, is equal to 0, and v1, derivative of v1 at x is equal to 0 is equal to 0. So I have two boundary conditions for V1, okay? But I don't have any boundary conditions for V2, right? But what can I say in the case, if I draw it right here, you see, let's draw it one more time here. So if this is a beam, and this is the deflected beam, this is my deflected beam, there you go, okay, and this is the neutral axis that we are trying to find this V, right, at any point. What can I say about point x is equal to 1, right? If you take x from left, then 1 is here, x is equal to 2 is right here. What can I say about point x is equal to 1? Well, I know that this deflection here is V2, and this deflection here is V1. At particular point x is equal to 1, which is this point, I have V1 is equal to V2, because my beam is not going to break. The beam is continuous. So at this point, I have one additional condition. What about the slope? Look at the slope. Let's use another marker, like green or maybe blue. The slope from the left, this is slope from the left, is identical to the slope from the right at this point. Because at this point, because the derivative exists and is unique, you only have one fitting line. So the slope from the left is equal to the slope to the right. Mathematically, dv dx, which is the slope from the left, mathematician put the minus for that, is equal to dv dx on the right. So what is my v minus? V minus is simply dv1 dx is equal to, the plus is dv2 dx. So I have two additional conditions. The first condition, the first additional condition, excuse me, the first additional condition says the V1, excuse me, I need to drink some water, I'll be back. The first additional condition says V1, which is the deflection just before point 1, is equal to V2, which is the deflection just after point 1. The second condition says the derivative or the slope, the derivative of deflection, which is the slope at point 1 just before that, which is d1 dx, is equal to the slope just after that, which is dv2 dx. So I have four boundary conditions. Let's label them in. Let's let's label them in a color. Where is my different colors? Let's use some sort of new color like purple. Yeah, so this is boundary condition 1, boundary condition 2, and this is condition number 3, condition number 4. So I have 4 conditions. So let's start integrating. So first let's start integrating this equation. So if I integrate that twice, I get 2 constants of integration, right? And if I then integrate that, I get 2 additional constants of integration. So how many constants of integration do I get? 4. How many conditions do I have? 4. So 4 equation, 4 unknown. Then I can solve for that, right? So the solution is a little bit more complicated than the previous test case, but the philosophy of solving is exactly the same. So let's go ahead and integrate the first equation. So I write d second derivative v1 dx squared is equal to 2k times x minus 1. Integrate that. First integration gives you dv1 dx is equal to 2k x minus 1 square over 2 plus c1. Okay, now I can apply the boundary conditions immediately right here. What is the first boundary condition? Look at actually equation number 2 right here. You see that? Equation number 2. It says dv dx dv1 dx at x is equal to 0 is equal to 0. Let's apply that. What do I get? I get 0 is equal to, put x0, you get 2k times, if you put x0, that becomes positive 1 over 2 plus c1. Then this becomes 0, will become 2k 1 over 2 plus c1. Therefore, this becomes 1k and c1. If you solve for c1 becomes negative 1k. Okay? So let's go ahead and integrate one more time. So if I integrate this equation now, I get v1 is equal to, this is 1k already, 2k divided by 2, 1k. So you get x minus 1 to 3 over 3 plus c1, which is negative 1k. So I change this plus to minus. So where is my pencil? Right here. So negative c1 is negative 1k, so you get negative 1k times x plus c2. Okay, and how can I find c2? Well, go back to this equation number 1 here. It says, you see equation number 1, or boundary condition number 1, says v1 at x equal to 0 is equal to 0. So let's apply this condition. So you get 0 is equal to, put x is equal to 0. So you get negative 1k over 3. You see, x0, negative 1 to the third power is negative 1. K over 3, negative 1k times 0 plus c2. This is 0. So c2 is equal to positive 1k over 3. So I completely found my v1 curve. Sometimes they become coupled, v1 and v2. But in this simple problem, I completely found v1 from my boundary condition, because I started from left and everything was known from left. Okay, so let's put them back together. So v1, put this c2 right here, this equation. Your v1 is equal to 1k over 3 x minus 1 third power minus 1k times x plus c2, which is plus 1k over 3. You don't really need to simplify it. That's your deflection curve versus x from x0 to 1. Don't forget the limits. This is only valid from 0 to 0.1. Okay? In fact, you can put equal here, less than or equal to 1, because the deflection curve is continuous. Now, I want to find v2. So what is the equation for v2? It's right here, right? So v2 is simply says the second derivative, according to the equation, the second derivative v2 with respect to x is equal to 0. Because the moment, look at it here, mx is equal to 0, right here. You see? Because of the moment diagram right here. You see that? The moment is 0. So I just simply substitute here, and then I have to double integrate that. The first integral of this equation is dv2 dx is equal to c3. There's a constant of integration because I already used c1 and c2 right here. Let's highlight them. Highlighter. I've already used c1 and c2, right? Then I need to introduce another constant. Let's call it c3. That's the reason I use c3. Okay, so here I have c3. Let's integrate this one more time to get v2. So if I integrate one more time, I get v2 is equal to c3 x plus another constant integration. What should I call it? Let's say c4. So this is a complete curve for my deflection between x is equal to 1 and 2. But the question is, do I have C3 and C4? The answer is no. But how many boundary conditions do I have? Or how many conditions do I have? Well, look at here. Equation number 3 and equation number 4. So I have two additional equations, two unknowns here, C3 and C4, then I can solve it. So the first equation says, equation number 3, it says V1 is equal to V2 at point 1. So let's write it here. It says V1 is equal to V2 at point x is equal to 1. So at this particular point, if I put x equal to 1, then I get V1 is equal to V2, right? And also, this was equation number 3, okay? Equation number 4, it says the derivative of V1 with respect to x is equal to the derivative of V2 with respect to x at point x equal to 1. And don't forget the x equal to 1 is exactly in the middle, right? So as at x is equal to 1, V1 is equal to V2, again at x equal to 1, these are two additional equations. The derivatives should be same too, right? So let's do that. So what is V1 at point x is equal to 1? Well, I already have my V1. Let's use a highlighter. This is my, let's see if I can get a bigger one. Yeah, this is already my V1. I already obtained it. So I can simply use that to find the value on the left hand side, right? So let's do that. Substitute 1 in this equation and I get V1 is equal to, if you put 1, the first term right here becomes 0. The second term becomes negative 1k times 1 plus 1k over 3. So this negative 3k over 3 plus 1k over 3 negative 2k over 3. So V1 at that point is equal to negative 2k over 3, right? So what about V2? So let's apply it, put it in this equation. So the left hand side becomes negative 2k over 3, which is V1 is equal to V2. V2, according to this equation, is C3 times x plus C4. But what is my x? My x is equal to 1. So I have C3 plus C4. Because x is right here is equal to 1. Right? So I have this equation. Can I solve it for C3 or C4? No. I need to have the extra equation, which is this equation right here. Okay? So let's find the derivative of V1 with respect to x, which is right here. Evaluate that, x is equal to 1. So all I need to do is to take the derivative of V1 right here. So dV1 dx is equal to 3 cancel out with 3, so you get negative 1k x minus 1 to 2, right? So it becomes 3x minus 1 to 2. 3 cancel out with 3, you get 1k, x minus 1 to 2. Negative 1k. That's your complete excuse me, derivative. That's your complete derivative when you're when your x is equal to 1. Excuse me. 1k x minus 1 to 2, negative 1k. Okay? So what happens if you put 1 here? So substitute 1 here. You get dv1 dx at x is equal to 1 is equal to, the first term becomes 0, negative 1k. There you go. Now going back to the equation, it says negative 1k. Look, I'm using this equation. Left hand side becomes negative 1k. Right hand side is the derivative of v2 with respect to x, which is c3. Take derivative of this with respect to x. dv2 with respect to x is equal to c3. Evaluated at x1 becomes c3. So this equation immediately gives me the value of c3, which is a fun thing, good thing. Now substitute here to get c4. So you have negative 2k over 3 is equal to c3, which is negative 1k, plus c4, right? Then solve for c4, you get c4 is equal to 1k negative 2k over 3, which is equal to, the first thing is 3k over 3, so it becomes 1k over 3. So c4 is equal to 1k over 3. So let's substitute c3 and c4 into v2. Then you get v2, let's write it here, is equal to, according to this equation, v2 is equal to c3 times x, and c3 is negative 1k times x, plus c4 plus 1k over 3. There you go. Highlight it. Now look at two highlighted area, v1 right here and v2. You see, these are the complete description of deflection at two different regions. From x equal to, let's use highlighter, yeah, from x equal to 0 to 1 for the first one, and from x is equal to 1 to 2 for the second one. And the problem is completely solved. Now in the next problem, I want to make this a little bit more complicated. In fact, I want to, instead of, you see this problem was kind of like, you have welt here, so you have two nice conditions here, both v and derivative is 0, right here. And then we had a load here. Well, then you take two intervals from here to here and then from here to here, and you solve it. So you get 4 constants of integration. Now I want to make this problem a little bit more challenging. Instead of that, I want to remove this wall connection and make this problem like this: you beam, okay, and then you have like a 2k right here. Let's put it in the middle. Let's put this 2k in the middle, like the previous example. So here is 1, here is 1, and 2k in the middle. But instead of wall, I'm going to put a pin here and a roller right here. Okay, flat. And then the question is, how do I find the equation of elastic curve right here? So in fact, I want let's call it from here to here V1. So V1 is the deflection at any x. Let's say your x is also from left, x. V1 is the deflection of neutral axis at any x. Then you have V1, and from here to end is V2, two separate regions. How do you find V1 and V2? Think about it. The next video will cover this problem.